We talk about the digital filters. So we talk about difference in equations, filter categories, then inputs and outputs relationships of filters in the time and frequency domain. So a filter can be built using a difference equation. So the difference equation is given by this simple equation here. So the general representation of a digital equation is that the output is a linear combination of past output values plus linear combination of past input values and the current input values. So that's a general representation of uh, a a digital filter represented in difference equation. So if we have this example, which is that the output is a linear combination of the past input value and the current plus the current input value. And we want to determine the response of the filter to an impulse response or to an impulse input. So this is the input and this is an impulse function. So we want to determine the response of the filter when an impulse response input is applied. And we assume that the past output values are from minus infinity is 0. So this is the representation of the impulse response. So it only has a signal, an impulse at 0. So the others from at negative and the positives, they are zeros. So the others is just at 0. It has an impulse. So we want to measure the output of the filter um, given this impulse response. So we'll look at when n is at different values. So starting from when n is -1. So using this equation, we put in -1 here. So -1, here's -2, and here's -1. So why -2 is 0? Because from the negative values, we assume that the negative values of the output is 0. So that's why it's 0. Then x -1. So from here, this is -1. It's also 0, which is equal to 0. So at n is equal to -1, the impulse, the output is 0. That's why you have 0 here. Then when n is equal to 0, we just plug in 0 into this equation. So you have a y -1 plus b x 0. So y -1. So we got y -1 here as 0. So that's why there's 0 here. Then b x 0. So this is the input. And this is at 0. So at 0, you have an impulse of 1. So that's why it's 1. B times 1 is b. So you have 0 plus b, which is b. So at n is equal to 0, the output is b. Then when n is equal to 1, we just plug in 1 here. We arrive at this equation. Then y of 0, we got y of 0 here as b. So a times b is ab. Then x of 1 from here, this is x of 1 is 0. So at n is equal to 1, the output is ab. Then at n is equal to 2, we just plug in 2 here. So you have this equation. So a1, we got a1 previously as ab. So That's why you have uh, a a times ab is a squared b. So that's why you have this. So if you keep on going, we can see a trend already. So when n is equal to 2, you have ba squared. So when n is equal to 3, you have ba cubed. So when n is equal to n, you have ban. So it turns out that this filter, this particular filter, is an infinite duration impulse response filter, otherwise known as IIR, infinite duration impulse response filter, otherwise known as IIR. So why is it called IIR? It's because the output, it depends on past values of the output. So that's why it's called an IIR filter. So an infinite duration impulse response filter. So we want to determine if this filter is a high pass filter or a low pass filter. And in order to do that, we are going to uh, convert, represent the filter in the, we are going to represent the filter in the frequency domain. But before we do that, we can as well plot, we can as well plot the filter in the time domain. So this is the output of the filter in response to an impulse response input. So this is when, because B and A, they are constant values. So when A is equal to 1 and B is equal to 1, this is the response of the filter in the time domain. So you have N here, and this is the output on the y-axis. But when A is equal to 0.5 and B is equal to 1, plugging these values into this equation, then changing the values of N, this is the plots you are going to get. Then when A is negative and you plot it, this is the values you're going to get. So it keeps alternating between negative and positive. Then when A is equal to 1.1, and that's when A is greater than 1 and B is equal to 1. So this is the this is the plot. So it's like a ramp function. So, but this, using this plot, we cannot really know if the filter is a high pass filter or a low pass filter. Though we know that is an IRR filter, so it's an infinite duration impulse response filter. But we don't know if it's an high pass or a low pass filter just by these plots and changing values. So the way we can know is when we convert to the frequency domain and we get the transfer function, then we make a plot, then we can then determine if it's an high pass or a low pass filter. So this is a equation we're working with and want to convert it to the frequency domain. So we assume that the input x of n is given by this equation. So representing that we have converted it to the frequency domain and the output is given by this. So we're going to plug in these two equations, these two assumptions into the original equation. Then if we do that, we get this equation. But in order to do this, we should note that yn minus 1 is simply putting n minus 1 here, which is given by this equation when it's expanded. So when we do the maths, collecting like terms, separating the inputs from the outputs, we arrive at this particular transfer function. So this transfer function will enable us to know if it's a low pass or a high pass filter. So this is the transfer function. Yeah. So let's say that B is equal to 1. So just B is constant. Because in all of these examples, B was set to 1, but it's only the values of A that was changing. So B is just a constant, but it's the values of A that would actually determine if it's high pass or low pass. So, but when we plotted it in time domain, we couldn't really get it if it was high pass or low pass. So let's try the frequency domain now. So we said B is equal to 1. Then remember that for low pass filters uh, allows low frequencies to pass, but it attenuates high frequencies, while high pass filters attenuates low frequencies and allows high frequencies to pass. So if B is equal to 1, so B is just the 0, so it's just a gain, it's just a constant. So you can set it to 1 or any value you like. Then we set F, the frequency, to 0. So this signifies like a low frequency. So if F is equal to 0, the transfer function becomes 1 divided by 1 minus A. Then if F is equal to half, so putting half here in place of F, so the transfer function becomes 1 divided by 1 plus A. Then if we set F is equal to 1, this indicates high frequency. The transfer function is given by this, which is 1 divided by 1 minus A. So where this representation just makes us to know, have an idea of uh, of the transfer function at low frequencies, mid frequencies, and at high frequencies. So you have this true equation. So if A is from -1 to 0, so if A is from -1 to 0, it's an high pass filter. How do we know that? So uh, this is the transfer function we've got in. So let's say that, let's pick a value from -1 to 0. Let's pick -0.9 as a value. So at F is equal to 0, we have 1 divided by 1 minus A. So using this equation and using A as -0.9, you have the transfer function becomes 10 divided by 19. Then at F is equal to half. So maybe let's say high frequency, the transfer function is 1 divided by 1 plus A. So remember our A is -0.9. So plugging it into this equation, you have 1 divided by 0.1, which is 10. So this is showing from this represents low frequency and this represents high frequency. So you can see that at low frequency, it's attenuated. The 10 divided by 9 divided by 19 is very low. It's like 0 something. But at high frequency, when the frequency began to increase, the transfer function, the magnitude of the transfer function is 10. So this shows that it's a high pass filter. So when A is between -1 to 0, you have a high pass filter. Similarly, when A is greater than 0, you have a low pass filter. So in order to prove that, we can choose any value greater than 0. Let's choose the same 0.9. So if we put it here, this represents low frequency. So 1 minus 0.9, that's 10. Then at high frequency, 1 divided by 1 plus A, that's 1 divided by 1 plus 0.9, which is 10 divided by 19, which is very low. So this is a low pass filter because at low frequencies, F is equal to 0. It's the magnitude or the transfer function is high. So it allows that to pass. But when the frequency becomes really high, it's attenuated. The magnitude, the gain is attenuated. So it's a low pass filter. So we've been able to determine based on the value of A, we to determine if this is a low pass or a high pass filter. But we are very sure that it is an IIR filter because the current output depends on the past output values. So that's why we know that it is an IIR filter. So we look at another type of uh, filter. So we call it the averaging filter. So it's given by this equation. So the output just depends on the inputs and the past values of the inputs. So this is a FIR filter, finite duration impulse response filter, because its output doesn't depend on the past values of the output. So its output just depends on the inputs. So that's why it is it is a FIR filter. So similar to the first question, we want to get the response of the filter at when an impulse response input is applied. So this is an impulse function. I want to get the output of the filter. So we take when n is equal to -1. So when n is equal to -1, you just plug in -1 here into the equation. So you get -1 here, -2, and here you have -1. So here is x minus q. So when you look at this x -1, then x -2, then x minus q, all of them are 0. So to give you 0. So at n is equal to -1, the output is 0. So at n is equal to 0, so you just plug in 0, 0, and 0 here. So you have this equation. So it only has an impulse at n is equal to 0. So that's why you just have 1 here. The others are 0, so which is equal to 1 over q. So at n is equal to 1, we plug in the values, and here it's only 1 at x is equal to 0. So the rest are zeros. So you still have 1 over q. At n is equal to 2, you plug in 2 here. So it has values of zeros everywhere. Only at when you have minus q plus 3. So that's when you have 1. So it's still 1 over q. Then at n is equal to q minus 1. So you just plug in q minus 1 here, q minus 1 here, then q minus 1 here. So when you plug in q minus 1 here, we are going to get 0. So it only has an impulse at this point. So your final answer is still 1 over q. Then at n is equal to q, so you have this equation. So when n is equal to q, you are just summing. So you've reached this point. So you are summing over this point from here to here. So it's 0. So you have 0. So given the pattern you observe, this is the time series plot of the digital filter. So it has 1 over q, 1 over q, 1 over q until when you get to q minus 1. So after q minus 1, the amplitude becomes is 0. So like I said, it's a FIR filter but we want to determine if it is an high pass or low pass filter. So we cannot, from the time plots, we cannot know if it is that. So we need to convert it to the frequency domain to determine that it is a high pass or a low pass filter. So in order to do that, we'll use the same principle we used in the first example. So we convert, this is the filter here. So we convert it to the frequency domain by representing, assuming that y of n is this and x of n is x ej 2 by fn. So we just plug it into the equation. Um, we collect like terms, we separate the input from the output, then we get this transfer function. So this is a transfer function here. So it turns out that this transfer function here is a sinc function. And we know that a sinc function is a low pass filter. So this filter is a low pass filter because the transfer function we generated when we converted it to the frequency domain, it's a sinc, and a sinc is low pass. So this is a low pass filter. So in this class, we talked about digital filters, which we represented by difference equations. So we talked about finding the impulse, the response of the filter to an impulse response. And we talked about if it's a filter is a FIR filter, which means a finite duration impulse response filter, or an IIR filter, which is an infinite duration impulse response filter. So this is what we've done in this